Okay, hello everyone. Today our topic is about using radioactivity and atoms and particles. Okay, so let's move to the first part about the usages about like here is tracers. Okay, so I guess tracers is not very familiar for you, but when you go to the hospital, when you go to a body check, you'll find you're using this apparatus, right? So in the hospital, you can find doctors using the tracers to check your body, whether your functions of bodies, whether the organs have a very clear shape, and if there's a tumor or like some other or like bad shaded in your body image, they'll find directly and tell you, oh, maybe here you have a problems, right? So I guess tracers just like using the like radioactivity, like using gamma rays, because gamma rays can have a great ability for penetration. They can penetrate your body and to find the inner part, right? Okay, so this is for tracers use. Okay. And another use is to testing for cracks and thickness monitoring. Okay. So maybe you can find if you're like design a microchip, right? You can find the size and you can find the scale for the microchip is very small. Maybe the scale is to a nanometer. And if you want to detect them, it's very hard for you to detect all the like microchips. So like using this apparatus, you can find using a control unit and a detector and using gamma rays, and you can detect very clearly, okay, because gamma ray is very a small like size particles, okay. So it can compared with nanometer, like 600 nanometer, 500 nanometer, it can just detect it. Okay. So it's not very difficult. And maybe in some other like fibers or like other like factories that want to produce it, it has to make sure that there's no information leak and there's no like any like in any process it cannot be damaged. Okay, so for here we had to use this apparatus like to testing for cracks. Okay. And another usage is for carbon dating. Okay, so here you can find maybe after some creatures like dinosaurs, they died down. Okay, so they just bodies are buried in the like dust. Okay, you can find here. So when they first buried into the ground, you can find the age is zero. Okay, so they can release for the carbon 14 like this radiation. But maybe after 4 years, after the carbon dies down, you can find maybe it turns into carbon like carbon 12. Okay, sorry, carbon 12. If it turns into carbon 13 or other kind of atoms, okay, so you can using a like radioactive detector to detect the radioactivity, find what is the age for carbon, okay. So you can find in maybe some museum, like in British, like in Germany, and you can find maybe in something like in China, maybe many places. They're using the carbon dating to detect what is the age for like uh, some like original things in the museum. Okay, it's very useful. Okay, so like maybe when the first time is maybe for 100% carbon, and maybe after for like 5,730 years. Okay, we said it's a half-life for the carbon, right? So you can find there's only 50% carbon of this. Okay, so if your detector just detect like 12.5% of carbon inside of this, you can guess that you just passes through like three periods or like three half time. So each half time is about 5,000 years, and using the three times 5,000. Okay, like this way you can find the age of the like the bodies in the museum. Okay. Okay, so the next part is about atoms and particles. Okay, so we just deep into and discuss about what is atoms and what is structure about particles. Okay, so we have said here, like here, you can find there's a like a nucleus in the center. We already said before, right? They are made by protons and neutrons, and many electrons are just surrounded with the nucleus. Okay, so you can just like on the right figure, you can find there's like electrons transferred at a very fast speed, and in the center is just nucleus. Okay. And maybe before this, a very famous story is about Thomason's plum pudding model. Okay, so in this plum pudding model, it's just as its name, right? Here's a pudding. So the pudding is made by the positive charge. Okay, and some negative electrons are just put inside in the pudding. Okay, so like here, you can find your electrons put inside the puddings. So you can find they're just arranged and they're like like maybe for randomly put in the pudding model. Okay, so in this way, it can just explain like why the total charge equals to zero and why there is like some positive charge inside, but we cannot determine whether if it is a plum pudding model. Maybe there's another structure. Okay, so this is a very famous theory. Before we like have like this orbit theory. Okay, so this is a very theory. You can just remind it. Okay, about Thomas's palm pudding model. It's just before the orbit like astronomy model. Okay. So how we determine if it's not this structure, and here we have experiment. We can call it a Rutherford nuclear model. Okay. So the scientist Rutherford, he is a very brave and he just come like make a cooperation with his student and to do this experiment. Okay. So after several years, he just using a alpha source to pass it through or like to make it as a very direct stream like this. Okay, so the laser like laser beams just like shoot out and to shoot out a gold foil. Okay, so please remember there alpha source is helium-2 nucleus, right? So it takes positive charge, right? Okay, so inside of the gold foil, you can just like make an enlargement and you can use in a side view. Okay, here is the wise of the gold foil. Okay, and you can find each particles like this way, right? And many positive charge right here. Okay, so he finds there are three phenomena or like three results. So most of the atoms just passes through and do not have a deflect. Okay, and a few alpha particles are deflected slightly, and a few alpha particles, maybe very few, like compared with this, is fewer. Okay, and bounce back and to just go through like this way. Okay, so what can we get in this experiment? First, we knew that there must be positive charge and negative charge in the particles, right, or in the atom. Okay. So based on the first formula we can find, because we said positive charge or like the same charge have the like repulsive force, right? So in the first situation, we can say, oh, maybe here most of the particles passes through very easily and there's no deflection. That means maybe in the center it's very small, or maybe it cannot become like this way. It cannot be scattered in most of the places in the atoms, right? So if it's gathered in all the places, it must be deflect, right? So here you can say, oh, here it is a center and it's very small. Okay. So first we said the positive charge is in the center of the atom. Okay, and it is very small. So there's no deflection and there's no repulsive force for most of the alpha particles. Okay, small size. Okay, so this is the first reason or first model we got, or first like a result. Okay, and second, using this way, you can find a fewer alpha particles are deflected slightly, right? So we can find maybe right here, like most of the positive charge are just like here. Okay, and you can find it very small, and if you want to shoot on this, you can just deflect. Okay, like this. And also the third phenomenon you can find, it just deflects or rebounds back. Okay, that means if we just very lucky to shoot on the center, right? We can find, oh, here's a deflection and it deflects like this way. Okay, so we can say, oh, here is how it rebound. Okay, so all the like phenomenon just gives an example or like gives this result. Okay, so you can also change the alpha source, like its direction and also its position. You can find maybe here, changes to another position, and also you can do this experiment. And you can find all the particles are arranged like this way. Okay, these are the positive charge. Okay, so we can start each atoms. They have a little bit like distance between each other, and the center is very small. Okay, compared with their distance and their size. Okay, like this way we can say this is the second like result. Okay, so based on this we can do this exercise together, like here for this problem. Okay, like in A is a figure 11 shows the passes of three alpha particles moving towards a single foil. Okay, four gold nuclei are shown here. The first question is on figure 11, complete the passes of the three alpha particles, right? So you can find in the first figure that the pass or the alpha particles helium-2 positive just shoot on the center of the gold nuclei, right? So it must be deflect, right? It must be deflect in the same pass, right? And you can find the second, the pass of the alpha particles, because it's positive charge, there's also positive charge. So it will just deflect, right? You can find there's deflects, okay. So here you can find it passes through the center, and you can find here this positive charge and this positive charge of their nucleus gives their force, and there's a force. Okay, so you can find the resultant force here is just like a blue arrow. Okay, so it just accelerates, but its direction doesn't change. Okay, so you can find maybe here this just moving at a straight line. Okay, like this way. So this is the three paths of our alpha particles. Okay. And second problem is to state the sign of the charge on the alpha particle. So we can say it's 2-unit charge, right? Because alpha particle is helium-2, 4. And 2 means a proton number and the positive charge number, right? And 4 here means a relative mass number. Okay, so finally we're choosing 2. Okay. And for B, you can find a nuclear notation for the nucleus of gold 198 is about 198.79 like gold. Okay. So here it says the number of electrons, neutrons, and protons in a neutron atom of gold 198. Okay. So first is number of electrons, right? You can find here. For the number of electrons, we can say, oh, right here, we have the same number with a prime number, right? So we can say, oh, here it is 79. And for neutron number, it using the 198, it means the total relative mass, right? So it means relative mass and also means a proton number added with neutron number, right? Because each proton number and neutron number takes one like relative mass, right? So total, if there's 198, that means the number together is 198. And also for 79, we knew that 79 means here we have the proton number, right? And also we can say, oh, right here, it equals to the positive charge. Okay, so here is 79. So we can say, oh, maybe for here, proton number is also 79, and the neutron number is using 198 minus 79, right? So it's 100 and like 21. Okay, so this is for this question. I think it's not very difficult for you. So just please remind using the like electricity, using the that knowledges and trying to find the paths that it deflects or like it's going through. Okay. So this is for today's lesson. See you next time. Bye.